So as Mohit said, I am a fourth year BSMS at IISER Kolkata, and since this is ISES, I don't have to explain what a BSMS is. Most of the places where I go, I need to explain it. Okay, so I'll be talking about rational points on various kinds of curves, and my research interest, as you already said, is number theory. So I'll be talking about rational points on various kinds of curves, but we will start with a very basic question, a very classic approach to finding all the Pythagorean triples. I'll explain what I mean by that, and okay, with that we will start. Thank you, Moitra, for arranging this talk, for bringing me in. I'll start sharing my screen, and maybe I should switch my video off now. Okay. So, okay. So, is the screen properly visible? Yeah. Okay. Okay. Thank you. So, as you can see, I'll be talking about rational points and Pythagorean triples. So, at first, so we will start with a very classic question, as I already said. So you know that Pythagorean triples are three numbers of the form, three numbers which can fit to be the sides of a right angle triangle. So, but here we will only restrict our attention to the integers that fit as sides of a right angle triangle. So basically, we want to find all the integer solutions to the equation x squared plus y squared equal to z squared. So any integer solution to this equation will correspond to a right angle triangle with its sides. So what to do this, we will, but as you can see, if x squared plus y squared equal to z squared, then you can multiply by any a on both sides, any integer a on both sides, and make it ax squared plus ay squared equal to az squared, which is the same as a square. I mean, you can multiply by a square, and you will get ax whole square plus ay whole square equal to az whole square, which means if x, y, z are solutions, then ax, ay, az are also solutions to this equation. So instead of trying to find all the solutions to that equation, it makes sense to find all the solutions in which the GCD of x, y, and z is 1. So because once we have all the solutions satisfying GCD of x, y, and z is 1, we can just multiply by a and find all the solutions to it. So these kind of solutions that satisfy GCD x, y, z equal to 1, these solutions are called primitive solutions. So, but before we proceed on to this, we will do one more trick, and this one more trick is we will divide by z square. And now we divide this original equation by z square, and we put x equal to small x equal to x by z, small y equal to capital Y by z. And this equation, as you can see, transforms to x squared plus y squared equal to 1. And this is a very familiar equation. This is the equation of a circle. So this is the equation of a circle, and as you can understand that any rational point on this circle, that is any rational solution to this equation, a rational solution is a solution which is rational, so a rational number, any rational solution to this equation corresponds to an integer solution to our previous original equation. So if we can find all the rational solutions to this equation, we can find all the integer solutions to our previous equation. But as you will see, as I have mentioned in my abstract as well, this will be done in a very geometric way, and to explain how this is done in a more geometric way, I'll divide my just give me a moment. So I hope you can see both the screens, and so one is x squared plus y squared equal to 1. So we plot this circle here. We have the circle x squared plus y squared equal to 1, and we want to find all integers, all rational points on this circle. So any rational point is basically a point both of whose coordinates are rational. So 1 comma 2 is a rational point, half comma 1/3 is a rational point, but let's say 1 comma e is not a rational point because both its coordinates are not rational. So also I'll urge you not to look at the left side of the Desmos graph screen because it contains a spoiler that I don't want to spoil before, but I need to keep it open because I need to use it. So once we have this, we can see clearly minus 1 comma 0 is one such solution. So minus 1 comma 0, this point is one such rational point on this circle. Clearly minus 1 comma 0 is. Now what we will do, we will, you may have seen something similar in elsewhere in mathematics, and you will be able to identify if you've seen it before, that we will use this point to generate all other rational points. So now let's say if uv is another rational solution, then we can join the 2 points uv and minus 1 comma 0, which is this line. So as you can see, if uv is one more solution, which is here, let's say uv is a rational solution. So if you join uv and minus 1 comma 0, if you cut a straight line through it, we get the line. The line is given by this equation, v by u plus 1 and x plus 1. And you can check in your home that these equations are indeed correct. I have written them indeed correct. So if uv is another solution, we just join these two and let the line pass through both these points. And this straight line has a rational slope because the slope of this straight line is v by u plus 1. We know, so the slope is rational because it's v by u plus 1, both v and u are rational, so this is rational. So this meets the y-axis at the point 0 comma t. So here's 0 comma t, as you have seen, you can see here 0 comma t, and this is precisely the point where this meets the y-axis. You can see it geometrically, you can also check it algebraically. When you put 0 comma t, it satisfies this equation. So it meets the y-axis at the point 0 comma t. And as you can see, this tells us a lot. Like the fact that it meets the point 0, meets the y-axis at 0 comma t tells us a lot. And what does it tell us is, once you have minus 1 comma 0 and a rational point u comma v, it meets the y-axis again at a rational point because t is rational and 0 is of course rational. So 0 comma t is rational. So once you have two rational points, they meet the y-axis. The line through them meets the y-axis at another rational point. So, but we want more. We want the converse of this to be also true. So, and luckily the converse is true. So any line through minus 1 comma 0, which has a rational slope t, the equation of that line is y equal to t into x plus 1. And if you plug this into 2 is, remember the equation of our circle, you get x squared plus t squared x plus 1 whole square equal to 1, from which you get these two solutions. X equal to minus 1 corresponds to our original equation. And this is x equal to 0, by the way. So I forgot to plot this. So x equal to minus 1 is our original solution. So we will discard this solution. And x equal to 1 minus t square by 1 plus t square. And when you put x equal to 1 minus t square by 1 plus t square, you get y equal to 2t by 1 plus t square. And as you can see, this is precisely the point. This is precisely the point that corresponds to u comma v that we have started with. So u comma v is this point. You can even see geometrically that this works. This is the spoiler that I was talking about. I didn't want you to see this solution before. But once you have this solution, you can have much more. So once you have this solution, as I said, so xy corresponds to 1 minus t square by 1 plus t square, 2t by 1 plus t square. And this form may be familiar to you. This form you may have seen in various other places. So this form is precisely the form that will give us the form of the Pythagorean triples, as you will see. And also, if you have seen the geometry that you just saw is nowadays in other parts of mathematics like projective geometry, like geometry and topology, it's called a stereographic projection. So this projection basically takes this point minus 1 comma 0, all points on the all rational points on the circle except minus 1 comma 0, and maps it to all rational points on the y-axis. So it creates a 1-1 correspondence, a bijective correspondence between all the rational points on the y-axis and all the rational points on this circle. So this is a pretty standard projection now, but this is a very classical problem, so it came up quite early. Okay, so by drawing all such lines of rational slope, we can be sure that every rational point on our circle has been counted. So these are all the rational points on this circle. Now we want to change these rational solutions into integer solutions. So this starts our integer hunt. We have done our rational hunt properly. This starts our integer hunt. So to hunt for integers, we will see what kind of solutions fit in our original equation. Remember, our original equation was x squared plus y squared equal to z squared. So can x and y both be even? It cannot, because if x and y are both even, then x squared plus y squared is even, which means z squared is even, which means z is even. This means the GCD of x, y, and z is no longer 1, which is a contradiction because we wanted GCD of x, y, and z to be 1. So we will see what are the combinations that are possible. Can both of them be odd? Well, not really. If you think about it for a moment, and if you're familiar with these things in number theory, that both cannot be odd, because if both were odd, then x square and y square were odd. And since x square and y square are squares, they are always 1 mod 4. Odd squares are always 1 mod 4. And this would mean z square is 2 mod 4. But z square is 2 mod 4 is a contradiction, because squares can never be congruent to 2 mod 4. It can either be 1 mod 4 if it's odd, and if it's even, it will be 0 mod 4. And that is, if you are not familiar with the notion of congruences, then it means that odd squares are always of the form 4n plus 1 or 4n. So just to make sure we are all on the same page, I'll show you a short animation to convince you that this is indeed the case. And this animation was created by someone called Satvik Saha. He's a very good friend of mine, and he's a very good programmer. So he created this thing. So as you can see, this is an odd square, and this animation immediately shows you that this is congruent to 1 mod 4, and this is an even this is an odd square, and you will see why it's congruent to 1 mod 4. Let the windmill complete. Yeah. Okay. So I hope it's understandable why it's 1 mod 4. As you can see, first it starts with an even square, which is 1 mod 4. Then it changes it to an odd square, which is an even square, which is 0 mod 4, and it changes it to an odd square, which is 1 mod 4. Using this windmill process. And okay, so if there's any problem to understand this, please ask me after the talk. So this kind of makes everything very very proper. So both odd is not possible. Can 1 be odd? Can x be odd and y be even? Well, it can be. Clearly, 3, 4, 5 is one such solution. Can x be even and y be odd? Of course, it can be. By symmetry, by symmetry they can be odd. That's also 4, 3, 5 is one such solution. So by symmetry between x and y, if odd even is odd even is possible, then even odd is also possible. But this symmetry, we will use this symmetry again and claim that if we only classify the solutions where, let's say, x is odd and y is even, that's enough, because we can just switch x and y to get another solution. So once we have done this parity analysis, we know the parity of the solutions. We will continue our integer hunt. And to continue our integer hunt, let's say a rational point xy is given and it's parameterized by t, where t is rational. You remember t was rational, and it's written in the form m by n in its lowest terms. That is, the GCD of m and n is 1. It's a standard way to represent rational numbers. So now plugging this in 3 was our original style, our original form, you remember. So plugging this into our original form, we get, you remember, 1 minus t square by 1 plus t square and 2t by 1 plus t square. So we plug t equal to m by n into our original form. To get x by z is m square minus n square by m square plus n square, and y by z is 2mn by m square plus n square. So if this is true, then there must be some case such that kx is m square minus n square, ky is 2mn, and kz is m square plus n square. But this means k divides m square minus n square and k divides m square plus n square. Because remember, x and z does not share any GCD, so k has to divide, does not share any common factor. So k has to divide m square minus n square and m square plus n square. But this means k divides 2m square as well as 2n square. But m square and n square doesn't share any GCD, so k has to divide 2. So k divides 2 means k is either 1 or 2. But if k is either 1 or 2, let's see if k can be 2. If k is 2, then 2x is m square minus n square, which means m square minus n square is 2 mod 4, which is again a contradiction, because same idea, odd squares can either be 0 or 1 mod 4. So if you put in all the combinations, you can never create 2 out of it. So k cannot be 2 as well. So k has to be 1. So, but what does k equal to 1 mean? You remember where we got k from? If k equal to 1, then x has to be m square minus n square, y has to be 2mn, and z has to be m square plus n square. And that is exactly the solution we got. And this remember is for x equal to odd, y equal to even. So if you just switch these two, 2mn comma m square minus n square comma m square plus n square, this gives y equal to odd and x equal to even. So this form, I guess you remember from high school, but I don't think you ever saw the proof that these are all the Pythagorean. You proved that these are Pythagorean triples, but you didn't prove these are all the Pythagorean triples. So the answer to our first question, original question, what are all the Pythagorean triples? That is all triples of the form m square minus n square, comma 2mn, comma m square plus n square, all triples of the form 2mn comma m square minus n square comma m square plus n square, and all triples of the form this multiplied by some integer a. You remember we divided by we put the condition GCD of x y z equal to 1, so we can multiply by any a and get. So we classified all the Pythagorean triples. Now, once we have done this classification, we want to move on to like mathematicians, we want to move on to more general cases. So more general equations and rational solutions to them. So, but before that, we will discuss some jargon just to make sure we are on the same page. So, rational points are points of the form p comma q, where p, q both are rational. The rational lines are lines of the form ax plus by plus c equal to 0, where a, b, c are all rational. So, q means rational. I would push everything. The rational conics are of the form this, where all the coefficients are. It's a conic where all the coefficients are rational. And there are some very short observations that a line passing through two rational points is a rational line. You can, I would urge you to check these algebraically. These are very easy exercises and very easy to check. So a line passing through two rational points is a rational line. Two rational lines will always intersect at a rational point. A rational conic and a rational line may not intersect at a rational point, because you can see y equal to x squared plus 1 and y equal to x plus 2, we intersect at x equal to 1 plus minus root 5 by 2. So these lines and quadratics were specifically chosen to give x equal to 3. So as you can see, a rational conic and a rational point may not intersect at a rational point, but two rational points always meet at a rational point, and a line passing through two rational points is always a rational point. So this brings us to our next question, our first bit of generalization. So we want to address the question of whether we can generalize these tricks to find integer solutions to any equation of the form x squared plus y squared equal to n z squared. So our original, for some integer n, our original equation, if you remember, was x squared plus y squared equal to z squared. So that was the n equal to 1 case. But now we want x squared plus y squared equal to n z squared. So what are all the solutions to x squared plus y squared equal to n z squared? So first we need to think whether there are always solutions to this equation for any n. Is there any problem? Is anybody wants to ask any question? Okay, fine. If anyone has any question, feel free to ask. So x squared plus y squared equal to n z squared for some integer n. This is what we want to find. And before that, we need to think what are all the integers n for which this equation even admits a solution. For example, this equation may not always admit a solution. For example, you can check that x squared plus y squared equal to 3z squared will never admit an integer solution. So in other words, there will be no integer points on the rational, no rational points on the circle x squared plus y squared equal to 3. So what are all the the answer to this? I'll give the answer out in a very uninteresting way, and I'll get to the proof. But a more interesting way could have been to take you through this equation and ask you about whether to find a pattern within the numbers that do admit a solution, to check like from 1 to 20 and see which numbers do admit a solution. But unfortunately, we don't have so much time. So I'll give out the answer, and the answer is very interesting. It is that this kind of an equation will only admit a solution if n is the sum of two squares. And if n is if you have seen some number theory before, you may start looking at a pattern, a very beautiful pattern, which I will soon unravel. But you may start seeing something here, and if you can see something here, it's very good. Your intuition should start tickling a little bit now. So we will prove that this is indeed the case. That this equation only admits solution when n equal to a square plus t square. So we want to show that this equation admits at least one solution. If it admits one, then it admits infinitely many, because of the same rational hunt that we just did. So we can just hunt for rational numbers, and we can have one solution and use it to project to all other solutions. So let's see that a squared plus t squared indeed satisfy this equation. So if n equal to a squared plus t squared, then x squared plus y squared is a squared plus t squared times z squared, which is sz squared plus tz squared. So x comma y equal to sz comma tz is a solution. This direction is easy. The other direction is also easy once you know a hammer, and the hammer is called Fermat's two-square theorem. So what Fermat's two-square theorem states, Fermat's two-square theorem says, in case you don't know, is that if any prime can, so if any number can be expressed as a sum of two squares, the only numbers that can be expressed as the sum of two squares are those the square free part of which is congruent to 1 mod 4. So the square free part is after you you break it into prime factors, you take as many squares out of that prime factor you want, and you look at the part that's left after you take as many squares out as you want. So that's called the square free part. And this square free part has to be congruent to 1 mod 4. This is Fermat's 2 square theorem. So we will use Fermat's 2 square theorem. And if this equation does, so we will use Fermat's 2 square theorem to get a proof. So let's say this equation does have an integer solution and non-trivial integer. Okay, remember there is one trivial solution, 0, 0, 0. And 0, 0, 0 is a solution we will never talk about in this talk. So we didn't talk about this solution before as well. So we will only look at the non-trivial solutions. We will not look at the 0, 0, 0 solutions. So basically we discarded the 0, 0, 0 solution when we divided by z square, when we divided the original equation by z square. So if this equation has a non-trivial solution x, y, z, then x squared plus y squared equal to nz squared, which means nz square is a sum of two squares. But this means by Fermat's 2 square theorem that nz square, the square free part of nz square, has to be congruent to 1 mod 4, right? Because this is Fermat's 2 square theorem. But z square being a square, the square free part of nz square is same as the square free part of n. So the square free part of, if the square free part of nz square is the sum of two squares, then the square free part of n must also be a sum of two squares. This completes the proof. So n can be written as a sum of two squares. Sorry, the square free part of n is congruent to 1 mod 4. I'm sorry. So Fermat's 2 square theorem is the square free. It can be expressed as a sum of two squares if the square free part is congruent to 1 mod 4. So if the square free part is of the form 4n plus 1. So this completes the proof that if, since the square free part of nz square is the same as square free part of n, this immediately completes the proof. So, but the next question that you may ask is, we know that if n is of the form s squared plus t squared, then this will admit a solution. But what is that solution? This is a very pertinent question that you can ask, and the answer to this is not very interesting. So to find out this answer is quite easy. You have one solution, you project it to the rational line, you find all other solutions what we did before. You can check in your home. It's not a very interesting expression. I'll give it out. This is the expression that x, y, and z takes, but not everything can be interesting enough. So you can check that this indeed satisfy this equation, and you can do the same thing. It should be left as an exercise for you. So it should be left as a very tedious exercise for you. So once we have this x squared plus y square equal to nz square, we can go to another degree of generalization, and we can ask about the equations of the form ax squared plus by square equal to cz square. This is what we'll be doing now. We will address another interesting question, and that is ax squared plus by square equal to cz square. When does this have integer solutions? And as you may have guessed already, that this has a very elementary. This is a. I mean, this can be answered in very elementary terms. This doesn't need very advanced mathematics, but it's not also as short as the ones that we discussed before. It's not also as easy as the ones we discussed before. So we can't discuss this. I'll give the solution out though. So we want to find at least one rational point on the ellipse ax square plus by square equal to c, and this is much more difficult than the last one, although it's quite elementary. It doesn't require any advanced mathematics. It only requires need to get used to things like Leceda symbols and staffing number theory. But it's very elementary. The proof is very elementary. You can check the proof. It's available in various places. It's available particularly in a book called Fermat's Dream. Fermat's Dream, Part 3, I guess, and the book is by Kato, Saito, and Kurokawa, I guess. So you can find the proof in that book. The answer is, I'll only give you the theorem. The theorem is due to Leceda, and Leceda's theorem says that if A, B, C are co-prime positive integers, then the equation ax squared plus by square equal to cz squared has a non-trivial solution if and only if this equation holds. And this equation, the fancy brackets in these equations are Jacobi symbols. And Jacobi symbols, in case you don't remember what Jacobi symbols are, I'll quickly let you revise through Jacobi symbols once. So Jacobi symbols, as you can see, are defined like this in terms of Leceda symbols, and this is how Leceda symbols are defined. So I'll give you a few seconds to just quickly recall these two definitions in case you don't remember, because maybe not everybody is familiar with this stuff. So maybe I'll give you 30 seconds to just look at these two definitions. Okay, I hope it's all right. I hope the definitions are clear. So, so once the definitions are clear, we return back to our original question what we wanted to discuss. And this is a theorem by Legeta, and this is that this equation will only admit a solution when this holds. And as I already said, this can be proved in elementary terms, but you need to use some very advanced trick. So this is one solution. This is one answer to this question. There's also another answer, much more elegant and much more sleek answer, let's say, and that is due to 𝗳𝗁. The theorem by 𝗳𝗁 says that a homogeneous quadratic equation in several variables is solvable in integers, not all zero. That is not trivial. If and only if it is solvable in real numbers and in p-adic numbers for each prime p. I'll not go very deep. I'll not go into this theorem by 𝗳𝗁 because I'm not sure whether everybody is familiar with p-adic numbers, but this is a more general way and a more sleek and a more elegant way to express what we have seen in terms of Legeta's symbols. It's a more general statement though. Once you have 𝗳𝗁's theorem, Legeta's theorem is almost a trivial corollary of it. So it just becomes a corollary of 𝗳𝗁's theorem. So 𝗳𝗁's theorem is like it's so elegant. You have to discuss this theorem in the context of this equation. When you are discussing this equation, you have to put this theorem out. You just can't resist. So this is this kind of answers our question. So first, the Legeta's proof you should check Legeta's proof out sometime if you want. So now we will move on to the next part of the proof and the next part of our talk, and that is Fermat's last theorem. So once we have generalized ax squared plus by squared equal to cz squared, now we want to generalize the powers. So what's the first generalization of power? The first generalization of power is x cubed plus y cubed equal to z. And as you know, this is Fermat's last theorem. So we want to know whether this has an integer solution, whether this equation has an integer solution. So of course, as you know, Fermat's last theorem cannot be proved very easily. And the answer to that is we are asking for whether there is a rational solution of the curve x cubed plus y cubed equal to 1. And this is a much more difficult question than whether there's a rational point on the curve x squared plus y squared equal to 1. And this is because of two very specific reasons. One is the geometry of this curve is not as clear as the geometry of the other curve. For one reason is that a line intersects a circle exactly at 2 points, but a line may not intersect x cubed plus y cubed equal to 1 exactly at 2 points. More often than not, it will intersect it at 3 points. So you cannot create the 1-1 correspondence that you could create in the case of a circle. So in case of a circle, you could create a 1-1 correspondence. Remember, here we can't do that. We can't project. And also, this is one reason. Also, another reason, as we have discussed, a rational point, two rational lines always meet at a rational point. But a rational line and a rational curve may not intersect at a rational. A rational conic and a rational line may not intersect at a rational point. So any rational line and this curve will not intersect at a rational point. So we cannot generalize. So what this says is basically we cannot generalize these two powers. So we can generalize it to the coefficients that we did. Once we have Legeta's theorem, we can generalize it to get all the solutions on the ellipse, we said. But we cannot generalize it to powers. And so we cannot generalize it to powers, but we can do something different. We can do something different, and I'll discuss it in short now. This is what I'll end with. So, but before that, I'll like to briefly tell you that in case you don't know, the proof that Andrew Weil suggested of Fermat's last theorem is a very, very advanced proof in elliptic curves and rational points, finding rational points on elliptic curves. So it's not as elementary as we are discussing now, but it does at the end up with these kind of stuff. Only much more advanced. So as you can see, like this is lighting the fire, so and allowing it to turn it into something big. So now we will discuss what we can do. We can't do this, but we can do something else. And that is we will discuss elliptic curves. And so you may ask, why are we considering rational points? And I'll answer that after I discuss elliptic curves. So elliptic curves are these specific kind of curves of the form y squared equal to x cubed plus ax squared plus ax plus b. So you can see these two elliptic curves on the screen. And elliptic curves typically look like either the left one, where it will have two different disjoint components, or this one, where it will have one continuous component. So if it has two components, it basically means that this has three real solutions, and this case is when this equation has only one real solution. So these are elliptic curves, and we will do a very weird thing on elliptic curves. We will try to find all the rational points on this elliptic curve, and to do that, we will define addition of rational points on this elliptic curve. So let's say P and Q are two rational points. We will join P and Q and extend this line to meet the elliptic curve again at R. It turns out that R is again a rational point. So if P and Q are rational points, if you join them and if we extend them to meet the curve at R, it is again a rational point. So the fact that this I'll share this because this is quite interesting. The fact that this is, R is again a rational point, joining two rational points and extending to meet the curve again does give us another rational point, is an observation due to Fermat. Fermat observed it for the first time. And we know that this is an observation due to Fermat because Newton thanked him in a letter, later thanked him in a letter. So as you can see, the fact that joining two rational points and extending them to meet the curve again at a rational point, it does meet the curve at another rational point. This is a fact that even somebody of Newton's caliber found quite surprising. So these elliptic curves really have these beautiful symmetries that even Newton finds surprising. Even someone of Newton's caliber found it quite surprising that this pattern does hold. So you can see how unexpected this pattern must be, but it does hold. You can check it. But that's not how we will define addition. We will do one more step, and what we will do is we will drop a perpendicular from R and allow it to meet the curve once again. That perpendicular to meet the curve once again. So this is the point that we will define as P plus Q. Now one may ask that when we say perpendicular, what do we actually mean? Like perpendicular to what? And the answer is that the definition is not completely as trivial as I told. The definition of this addition uses a particular thing in projective geometry. And this specific thing in projective geometry is called a point at infinity. So this is the only thing that, like, if you don't know projective geometry, this is the only thing that you can take for granted for now. So what we do in projective geometry is we have R2, we have the plane R2, and we add one more point to R2. We call it the point at infinity. We literally call it infinity. So the way we are defining this, so we want this curve to lie in R2 union that point infinity. And the definition of addition of points on this elliptic curve is you have two rational points P and Q, you join them. You extend that to meet the elliptic curve once again at R. You join R and the point at infinity. You extend that line to meet the curve once again at another point. That is the point you will call P plus Q. So as you can see, it's a fancy way of saying drop a perpendicular from R, but to make it rigorous, we have to do that. So maybe it's not a completely correct statement that we have to do this only to make it rigorous, but there are other uses, but I can't discuss those technical uses without actually going into projective geometry. So I don't want to actually go into projective geometry to talk about this. So just remember for now that this is the definition, that when you have P and Q, you extend it to meet the curve once again at R, you drop a perpendicular from it, you get another point. That is the point you name P plus Q. So this is how we define addition on elliptic curves. And you may ask why this definition. So it may look like a very random definition, but the answer to that is this definition carries an extremely beautiful symmetry of the elliptic curves. And that symmetry is, if you let the if you define the set of points on set of rational points on this elliptic curve to be gamma, and if you have addition defined like this, then gamma with respect to this addition forms a group. And you can check that gamma forms a group by checking that this is, and gamma not only forms a group, it's an abelian group. So you can check that this is abelian, it's trivial, you can see that it's abelian just by the definition. And you can check all other properties of the group law holds, all other group laws hold, only geometrically. So you can only use this definition and play around a little bit to see that the group law, all the group law properties indeed hold. But that's not all. We have even more. It's an abelian group, and it's also finitely generated. So in case somebody here doesn't know, is not familiar with group theory, so what finitely generated group means is that you can take only a finite number of points on this curve. You can take only, there is a finite set of rational points which can generate the whole group. So if there is a finite set, over which you can repeatedly apply the addition operation and generate the whole group. So I'll discuss these two theorems. And these two theorems are so beautiful for me that I have really named this slide love poems. So I'll be reading out a couple of love poems to you. I hope you enjoy them. So the first poem is, of course, Model's theorem, and which is what I just discussed. So let C be a non-singular cubic curve. So cubic curve, and non-singular basically means that it doesn't have any quote unquote bad points. It doesn't have any singularity. So any cast for singularity and stuff like that. So quote unquote bad points. So let C be a non-singular cubic curve with rational coefficients. Then the group gamma that we were discussing, gamma is a set of all rational points with the operation of addition that forms a group, and that is finitely generated. So this group gamma is finitely generated. This is already a very, very surprising fact. And to prove this, we need another theorem, which is called the Nagel-Luth theorem. And that theorem also classifies a lot of rational points on it. And the Nagel-Luth theorem says that if you have this elliptic curve, y squared equal to x cubed plus ax squared plus bx plus c. So if this is a non-singular cubic curve, and if you define d to be the discriminant of this cubic polynomial, which is defined as this, as you can see, this is the definition of d. And this definition of d may look a little random, but it actually comes from a very specific part. I don't want to discuss this now, but it comes from this really represents discriminant. So if p equal to x comma y is a rational point of finite order. Finite order is if you apply x comma y plus x comma y plus x comma y plus x comma y, there will be a point where it will change to identity. It's finite order in the context of group. So if x comma y is a rational point of finite order, then either x y are both integers or y equal to 0. Then x y are both integers, and either y equal to 0 or y divides this system. So you can see what Model's theorem does is Model's theorem says this group is finitely generated. So you only need to know information about a finite set of rational points to know information about the whole group of rational points. And what Nagel-Luth theorem says is once you have a rational point and you know that it's a finite order, you can classify it even more. You can even say a stronger statement that x and y has to be integers. And once you know x and y has to be integers, that's not all. You also know either y is 0 or y divides d. And d is an integer, remember. So more often than not, there will be very few integers dividing another integer. So you really restrict your choices. Your choices really get very restricted. So x and y are integers, and either y is 0 or it divides d. So at this point, after we have discussed both of these, you may be asking why are we talking about rational points, a question that we have referred first. And the answer to that is not only that this gives us a lot of beautiful mathematics, and it gives us it gives us really a lot. As I told you, these elliptic curves and rational points are something Andrew Wiles used to prove Fermat's theorem. Only much more advanced. So this is not the only use. This is not the beauty is not the only reason. There is also another reason, and that reason is elliptic curves are very important in cryptography. So it's used in the context of cryptography. I wish I could have talked a little bit about how it's used in cryptography, but I don't want to get out of this talk more. So I'd like to restrict the talk till here only. And you may be asking what are the proofs of Model's theorem and Nagel's theorem. Well, the proofs are quite advanced, and proofs are quite involved. Not very advanced though, but pretty involved. And maybe some other day I'll come back and discuss the proofs of these two theorems. I want to discuss the proofs of these two theorems, but I'll keep it to some other time. So with that, with the usefulness of this in mathematics as well as in other parts, in cryptography, etc. And cryptography, as you know, is keeping your mail safe. So it's elliptic curves are indirectly keeping your mail safe. You can think about it like that. So with this, I'd like to end my talk. So with this, I'll end my talk. Thank you. So I'll be very happy to take any questions that you may have at this point. So please start asking questions. I hope you enjoyed the talk. The most generalized one. Yeah, exactly. As no, I don't think there will be any geometric approach that will come into play here, because as we have already seen, x cube plus y cube equal to z cube already restricts a lot, already restricts us from using geometry. So if we want to generalize the powers, and if your k1, k2, k3 are like more than 2, then then we will already run into trouble. And there is one answer to this question, I guess. And I don't know whether I don't want to say this answer because I'm not exactly sure about this. There's something called, if I hope it's Hilbert's 10th problem. I may be a little bit wrong. And this problem is whether there exists a general algorithm. Hilbert's 10th problem is whether there exists a general algorithm to find out all the rational points on a curve. And it has been solved, and the answer to this is there doesn't exist any such algorithm. So there cannot be one principle that will give you all the rational points on any curve you want. So there just cannot be any algorithm that will work for all curves. So as you can see, we already get restricted to these kind of curves. And as far as I know, I picked this up from a talk by Monjul Bhargav, who also works in similar fields. As far as I know, the geometric principle, like forget geometry, like we don't have a precise answer to the question you asked, not even using advanced methods. So we only have a precise answer in the case of linear and quadratic equation. So we don't know precise answers to more than that, as far as I know. Yeah. Hmm. Yeah, this starts falling into algebraic geometry after some point, because after some point you cannot handle the geometry if you don't know enough algebra to handle that geometry. So after some point, this kind of stuff goes into geometry. And I don't know whether I should say this, but there's also a related question, not a related question, a more general question, which is called the Barch and Swinnerton-Dyer conjectures. Yeah, so yeah, so yeah, it's one of the millennium problems. So it's the Barch and Swinnerton-Dyer conjecture. I would have discussed this if it was not about more elementary stuff. So if I ever discuss proofs of model theorem and Nagel's theorem, I can go into Barch and Swinnerton-Dyer conjecture a little bit. So that's one conjecture that still remains unsolved, and Monjul Bhargav is one of the many people working on it, so trying to crack it. It's true for one two third. Yeah, it's true for two third, almost 66% of cars. Exactly, it's true for that's the most advanced. I guess it's in 2015. 15, yeah, exactly, exactly. Gets right. Uh, yeah, also I guess there's one Abel lecture by Monjul Bhargav, and the lecture is named "What is the Barch and Swinnerton Diamond?" Yeah, in 2016, I guess. Yeah, yeah, exactly. On the occasion of Abel Prize of Whites, exactly. So, and the paper you mentioned, the
Yes,
paper
one
you,
more
oh,
question.
yeah, sure,
Yeah,
go on.
so my question was that as in the as being is being shown in this slide, the problem with cubics is that a line generally meets a cubic in three instead of 2 points. So
And
if
also,
we
it may
can
not meet at a
find
rational point.
yeah, so if there is a cubic which is like a convenient one, so which so I can find one rational point on the curve, and then I can get lines which only intersect at one other point. So basically, I can project the cubic into the line. If we can do that, then then can it be solved in general? All solutions can be found.
Um, that's an interesting question. See, there are two kind of constants here. One is that it doesn't intersect at a rational point, and another is a line. In case of a circle, the line intersects the circle at 2 points. So there was this. You had one initial point, and it intersects a circle at only one other point. Here, it will
Yes.
intersect the cubic at two other points.
Yeah, so that was my
So
question. If we could modify the question, like the cubic was a like a special case, a particular kind of cubic where the intersection is with only one other point, then can it be solved?
no, that kind of cubic doesn't exist. More like most often than not, you won't have a cubic where a line will intersect only at 2 points. You can have a cubic. I don't know though. I mean, I'm guessing you can have a cubic where lines passing through rational points will again meet. Rational lines passing through a rational point will again meet at a rational point. You may have a cubic like that, but I am
Okay,
pretty sure you will never
so
have a cubic where a line will meet at only at another point. So there will be lines which will meet at 3 points. That can't be.
okay,
That can't
so
happen.
so there are general cubic equations which have been completely solved, right? May
Yes,
not be
but they
this
have used.
particular cubic.
Yeah,
Okay.
yeah. No, this particular cubic has also been solved. It has been solved that this particular cubic doesn't have a solution.
Oh yeah. So I'm asking, like, there are cubic curves which has solutions, and all solutions have been found.
Uh, there are cubic curves which have solutions and all solutions have
Rational
been found.
solutions.
Is
Is
yeah,
that true?
yeah, maybe. I'm
Oh.
not sure whether you can tackle all cubic curves, but
No,
there
no,
may be
not
some
all, not
cubic
all
curves.
curves. No, yeah, some. My question is
Yeah,
about some
so there
cubic
may
curves,
yeah
not all.
there may be some cubic curves where all solutions have been found. Maybe yeah.
Oh, okay, okay,
Uh,
okay,
I would if I'm to guess, I would guess that there is.
okay.
So yeah. And also the paper that Moitio was discussing right now that came out in 2015 by Bhargav and somebody else, I guess. And that paper, like you just said that we couldn't extend anymore, we couldn't progress any more than that. Like the idea of that paper was to put all the machinery that we know into the BSD context. Like all the machinery that we have developed so far, put it into BSD and look at how much we can get out of it. And that's a solution that we got out of it. That is, it's true for 66% of the problem. So that's like it's like literally the boundary. The boundary was set at there. So now you need some other machinery to even go 1% higher. Yeah. Exactly. Exactly. The rank comes into question. Like yeah. So okay. So thank you, Moitra. Thank you for arranging this. So I'll stop my presentation now. So.